has demonstrated for us the innovative combination of additive manufacturing and digital design. So PGMs can be used in the fashion industry and also in the chemical industry, medical industry, etc. So it's going to be a whole new era. And also in face of the challenges posed by subjective manufacturing and long-term challenges such as complex structures and instability during the technological process, etc. This can be a very good solution. And also to answer these challenges, we will have Fei Zhuge from Ningbo Materials Institute to talk about all-optically controlled memristors for artificial intelligence. Hello, everyone. So the topic for me today is a little bit different from what I usually do in the past. I specialize in chips, to be more specific, brain-inspired chips for artificial intelligence.
Well, as you may know yourself, that artificial intelligence has increasing applications in the human society, and I believe that every day your life is closely related to artificial intelligence. You use it directly or indirectly. Traditional artificial intelligence was realized via computer and algorithm. So basically, it's based on the separation of computation with storage. In other words, it was based on traditional structure by separating CPU from memory. In other words, most of the time, energy is consumed for data transmission, and meantime is sequential. In other words, can only deal with one task at one time. It has other disadvantages, including slow speed, high energy consumption, and large size. So traditional artificial intelligence is increasingly hard for traditional artificial intelligence to be adaptable and to meet human needs in this big data era, because we need real-time handling and processing of large amounts of data. Human beings and human brains, as you may know yourself, represent some biological computers. What are the characteristics of human brains? It's mostly based on the neurons and the synapses, so it's able to do automatic and spontaneous learning and memory. So we have this brain-inspired computing. Brain-inspired computing features the integration of computing and storage. In other words, both are realized via neurons and synapses. Inspired by human brains, people start to have this idea that we want to simulate the way human brains work. In other words, I want to use electronic and optical components to build a brain-inspired computing machine with the advantages of integration of computing with memory and the ability to perform several tasks at the same time. What does that mean? It means that you can read, you can see, you can talk at the same time. That features simultaneous execution of tasks, which is different from the current computers, which work in the way of sequential performance of tasks. Such computing has other advantages in that it's fast, it consumes little energy, and is small. As for Memristor chips, as you know that you are all familiar with electron resistance, capacity, and sensing, they represent the three basic electronic components, and Memristor represent the fourth type of basic electronic components that have several advantages, including it's capable of simulating synapses and neurons in a very good manner, and it has dual-end structure, meaning that it's capable of integration at high density, and it's also compatible with traditional semiconductor and processor menu technology. An overview of the research on memristors as early as the 1970s, people started to do research on that. However, traditional memristor has disadvantages, including poor stability and severe draw heat. And in recent years, people started to switch attention to the combination of optical and electronical memristors. It has some advantages, however, still it faces the similar or the same challenges as was before. AOC memristor. AOC technology is capable of dealing with the stability issue in this field. What does AOC mean? Is that the entire stat and all the electrical resistance is driven by optic, and it doesn't have any change at the macrostructure level. It doesn't generate any Joule heat. In other words, it can address the stability issue, and its power consumption is very low, it's minimal, and achieve the integration of sensing, memory, and computing. It can have extensive applications, including being inspired computing chip. It can be applied to a new generation of artificial intelligence vision system. As for the AOC Memristor, there were a lot of inabilities to achieve it. So there are a lot of paper talking about the advantages of AOC Memristor. The thing is that we can't make it a reality. So last year in 2021, we were the first to make it a reality. We were the first internationally to produce the AOC Memristor. Why we are able to do things that other people aren't able to do? That's because we use a new structure based on IGZO. IGZO is a sophisticated material, but we were the first to use IGZO structure. So we use both oxygen-rich IGZO as well as oxygen depleted IGZO dual layer structure. As a result, we are able to make it purely electronic. This working mechanism is very important because if you use light to driving, and if you want to do it, it must be purely electronic. It can't involve any migration of ions. Otherwise, you can't do it in a purely optical manner. Another feature of our AOC Memristor is that it has broad spectral response properties. In other words, both in terms of visible light and near-infrared spectrum, our Memristor has very obvious, consistent optic-electronic conductivity, which is also very important because for the enhancement of electricity conductivity, we use short spectrum light. For the reduction, we use long spectrum light. So the broad spectral response represents a very important precondition for us to make the AOC Memristor a reality. While the most difficult parts to achieve or to build AOC Memristor is the light-induced decrease of device conductance. If you are familiar with this field, you know that for any semiconductor material, when light is shed on semiconductor, usually the concentration of electrons increase. As a result, its conductance also increase. That's universal to any semiconductor material. This is something that's beyond imagination to all of you because when light is shed on certain material, the conductance of this material decrease. In other words, the concentration of electron on the surface of such material decrease. This is something beyond the widest dream of anyone, but we were able to do it. We did continuous lighting, and we did light pulse model. So on both model, we were able to bring down the conductance of this component, which is the most critical part for us to make it reality. As for why, even if with the lighting of long spectrum light, the concentration of electrons decrease instead of increasing. Why? Well, because this represents some sort of new phenomenon that we accidentally identified. We don't quite understand the mechanism behind it, but according to our thinking, it might be that on the light of short spectrum, there's some sort of competition in between oxygen vacancies and electric ionization. So which one dominates determines whether the conductance will increase or decrease. Of course, I'm not going to go into the details of the mechanism. Based on this, we are able to create AOC Memristor, and we use blue light to increase the conductance of this material, and we use infrared light to bring the conductance down, and we use light-induced conductance that has the advantage of stability. We also, based on the AOC Memristor, achieved simulation of learning behaviors of the human brain, which represent the most important learning function of human brain, called STDP. We managed to make it a reality. As for the AOC Memristor for novel visual systems, most intuitive, most straightforward application is for us to be applied to the new or to the novel visual system. For the novel visual system. If we use AOC Memristor to build a system, what advantages do we get? Firstly, we achieve the integration of sensing, memory, and computation, as well as it's responsive to external light. It's able to sense external light. In terms of memory, data can be saved. In other words, the change of state can be memorized. In terms of computing, the information that you sense is able to be pre-processed via our system, followed by more in-depth processing later on. So if the AOC Memristor is used to form a matrix, the single matrix alone is able to allow us to achieve the integration of sensing, memory, and computing. So here I have to mention something that you have contact day in, day out, which is the camera, including facial recognition. So what are the characteristics of the existing camera? The separation of sensing, memory, and computing is the defining characteristic. In other words, for sensing, it requires separate camera. For the processing, you need CPU. For memory, you need RAM. In other words, the existing system features the separation of the three physical processes of sensing, memory, and computing. What does that mean? Most of the energy and data is consumed in between the transmission of the data among the three units. Compared with traditional visual system, we are able to achieve the integration of sensing, computing, and memory. In other words, we turn the previously separate units into a single chip. What benefits do we get from such integration? It avoids any transmission of data among different units. As a result, it saves time and also increases speed. On the other hand, energy consumption is lowered down dramatically. On the other hand, because it's all-in-one, the size is much smaller. I believe that's the most straightforward and fastest application of our AOC Memristor. Well, I've covered everything about the AOC Memristor. Let me just give you a summary. We have this special dual-layer structure, and we combine it with the platinum metal's unique power function for us to achieve this AOC Memristor. The mechanism is very important as it's pure electronic, and our research just opens up a new window for the research and application of the entire field of Memristor. Our AOC Memristor is able to integrate sensing, memory, and computing, which is conducive for us to build the next generation of artificial visual system. What's more important for our next phase of work is that in the past we used dual structure oxide, which is rather complicated to produce, but recently we have switched to single layer oxides. In other words, we only need one ZNO layer to achieve or to make AOC Memristor, and the material's robustness is very good. In other words, well, here I've just listed several. I've listed 5 target materials that we use as raw materials. As you can see, they differ in color, they differ in properties, because we bought them from 5 different companies. So these materials, they have huge differences with regard to the color and original electric resistance properties. Despite that, the material that we are able to produce with each and every of these material had very good robustness with repeatability of 100% with regard to the performance of the device, attesting to the robustness of our procedural, our process, and our material. So based on this, we have put in place a very simple artificial intelligence simulation network for the recognition of image with precision exceeding 90%. And we are also able to achieve all the 16 different types of Boolean logic, all 16, which for follow-up applications in semiconductor and chip manufacturing is very important. So recently, our most recent work features the use of AOC Memristor to build 1K size chip. Well, this chip at the physical level from the perspective of hardware is capable of doing such processing functions as extracting features from images, as well as other processing functions visually. Now, the thing is that before we developed this AOC Memristor, we did a lot regarding producing electrically driven Memristor. So one of the reasons we were able to become the first to develop AOC Memristor is because we have technical build-up from our research in electrically driven Memristor, including our understanding of the mechanism. All these are very conducive for us to develop the AOC Memristor. So this slide showed you our previous work with regard to the development of electrically controlled Memristor with filamentary mechanisms. In the slide, I've given you some explanation about this mechanism with our original work. And this slide showed you electrically controlled Memristor with purely electronic mechanism. This is very important. It's critical, as mentioned, that in order for such Memristor to be purely electronic, it must be electronically purely 100%. It doesn't involve any ion migration. If ion migration is involved, then there is no way for us to achieve AOC Memristor at all. In no way will we be able to do it. So we spent a couple of years doing research work, and based on our research in electrically controlled memristors, we became the first ahead of any other counterparties in the United States and Japan to develop the AOC memristor. So most of the innovative work doesn't come overnight. It requires multi-year build-up and accumulation. Only in that way will you be able to make such things a reality. Thank you very much. So much from me.